people who are willing to learn during holiday. Normally, people don't want to learn during holiday, but actually, there should not be a holiday. It's Labor Day. Yeah. So I believe we should be laboring more. But thanks for coming. I think let's do it instead of trying to look for a class. As I said, this single topic discussion and analysis of a computer communication network, we have to cover quite a number of topics, about 4 topics, which actually can enable you to discuss and analyze a computer communication network. And I'm starting from the assumption that you may not have covered that, but I will a bit fast, yeah, because as much as you haven't covered specifically the same topics, you must have covered those issues in introduction to computer network. Introduction to computers, or whatever you call it in the university. You also notice that I've sent you an assignment, and I sincerely apologize for sending you assignment 1 this late. It's supposed to have come earlier. So just that I decided to give you 2 assignments. Initially, I wanted to give you 1 assignment, which was basically designing a campus network. But initially, I don't think maybe I saw like it's getting a bit late. I don't want to give you. I better give you that last minute, but you better have another assignment. So instead of the standard 1 assignment, you are going to do 2 assignments. The one I sent you, and the one which I will send you after today. I believe you have mastered enough knowledge to start the design. Just a simple campus network. Yeah. But to design that, you need certain background, and one of them I got will be network devices and network media. But I still remember that I think we are not finished with the network protocol architecture before we go to basically this means OSI model, because there are many network protocol architectures, but we'll be looking specifically at the OSI model, and we only look at that one, and probably without going to details, we might look at another one model, the TCP IP model. Then from there, we can move on to network devices and network media, because if you have to design a network, you need to understand protocols, yeah, and then you need to understand how you choose the media, yeah, and of course how you choose. You need to have a basis of choosing the media and choosing the devices. Those are the most important parts of the network, and of course now the protocol that enable those devices to communicate. Yeah. And then of course we are talking about network. We are talking about analysis, so you also need to understand what are the usual network performance metrics, and we are also looking at, and of course you need to know what are the issues that affect performance in a computer communication network, and that's why we have also put another topic called flow control, congestion control, because those are some of the issues that affect communication. So I'll just try to explain, and probably apologize for the many topics, because they may sound like discussion and analysis can be covered in 1 or 2 topics. Normally, that only happens when you have a background in that particular unit. But I looked, whatever choices we had, you didn't have any background, so whatever choices we had, it means we had to cover quite substantial content before we can do this discussion and analysis. So I think we started looking at the network protocol architecture, and I think why we didn't finish is because we had started looking at a small introduction. I think we looked at the introduction. Now, for those who attended the last class, just I would like you to remind me exactly what you can remember in this network protocol architecture. Somebody can guide us, who is willing to, where did we reach on this particular network protocol architecture? Did we finish? Are we in the middle? Are we at the start? Volunteer. Before I volunteer somebody.
Okay, what I remember, or rather the thing that has stayed with me, is one, the mnemonic. All people seem to need data processing, and then earlier we were talking about PDU and SDU, where when you go a layer lower, you get the PDU.
Okay, that's what you can remember.
Yes.
Then I can see we had just started. We are not gone very far. So we have not started discussing various layers. Does somebody have a different view from somewhere else? Like maybe you went up. Because then we can start there. We can start by understanding the PDUs. Because we are going to refer to the PDUs a lot. That's why I thought of talking about the PDUs. Therefore, we were here. PDUs and SDU. But actually, PDU just means the basic unit at a particular layer. And the SDU means that part which is enclosed in that particular layer, which means when you talk of the SDU, then you're talking of the PDU of the upper layer. It is the SDU minus the header. I think that's the best way to put it. Before you put the header at a particular unit, then you have the SDU, which of course it means it is the one that came from the upper layer. Yeah, I think we have understood that concept. That if you have a SDU, you have a PDU, you have a PDU in this particular layer. Let's say it's layer. Let's say it's a layer 4. We are going to see which is layer 4, and then in layer 3, which is the lower layer, you remember at the transmitter, you're going from the higher layer to the lower layer at the transmitter, because the upper layer, the topmost layer is layer 7. That's where you access the network. That's where you get into the network. That's where you have that is the entry point into the network. So you are going down. So if this is layer 4, which of course has a header, yeah. So when it comes to layer 5, this becomes, so this PDU becomes the SDU of this layer, and then you have to add a header, and it becomes the PDU of this layer. Yeah. So what we are going to refer to mostly is the PDU. Yeah. What are those PDUs? What are the protocol data unit, the basic unit of that layer? What is it called? Because it will be important. Because when especially when you start the transmission, you're going to find that the PDU at layer 2, which is a frame, is very, very critical in understanding how communication happens in a network. So now that we know what are the PDUs, we can look at the different layers. We can start with the application layer. This is the layer that gives the users the access to the interface to the network. Yeah. So this is an entry point of the network. So once you have data to send, and of course that data to send must be, it could be a message. Yeah. It could be a message. Then when you come to the application, you give that message some header, and of course what the header does, the header is trying to communicate to the, I think before we proceed, let's understand this what I've drawn here. What I've drawn here, this is at the sender. So you find at the sender, oh, that's good. At the sender, you have all the layers. At the center, you're going to have all the layers. Yeah, I think we did talk about the why it's layered, because when it's layered, it means you can actually decide to, for manufacturers, for example, they can decide to deal with just specific layers. They can decide to just, for example, manufacture a device at layer 2, and that device will link at another device from another manufacturer at layer 3. Yeah. So once it is standardized and is layered, it doesn't matter at which layer you operate from. You make your device in layer 2, it will work with another manufacturer's device at layer 3, because it's standardized. And it also means now you don't have to make a device that works in both layers. For example, why I'm mentioning devices is because when it comes to devices, we are talking about these 3 layers, physical devices. Otherwise, this one is just software. These 4 layers is simply just software. Yeah, but what we are saying is we keep on adding functionality as we are coming down to the lower layer. We keep on adding functionality, and those functionalities, they are meant to communicate with the other side, with this end. Yeah. In fact, these 4 layers, we call them end-to-end layers because they don't have this part. Now, before you understand the end-to-end, of course, what happens is wherever this is A communicating with B, where A could be in Kenya, in Nairobi, and B could be in Mombasa, or A could be in Nairobi and B could be in Europe, or A could be in Nairobi and B could be in the US. It doesn't matter. The only thing that will increase, it is these ones. What these ones, we are supposed to do them like that. I do only two net. I think normally, of course, these devices, depending on the technology, could be only having these 2 layers, or you could be having the 3 layers. Yeah, because you find even in IP technology, sometimes you're going to have IP technology. It means you have this IP network, you have this network layer, but you find even that IP technology, in some parts, it just includes inside a layer 2 technology. Okay, that's deep, but so you might have some areas where you have got devices with only 2 layers, and you might have devices with the 2 layers. I mean, with the 3 layers. When there's only 2 layers, that would be like a switch. A switch would have these 2 layers. A router would have these 2 layers. I mean, these 3 layers. Of course, what happens, it doesn't have much functionality for layer 2. But you have certain functionality, because once the packet comes, for example, it has come from here and it's coming here, you still have to have layer 2 functionality. You have to check into that packet. Yeah. But we are going to see how that happens. Eh? So what you are saying is here you are going to have very many of these, yeah, these devices here, which may either be switches or routers. If you have 2 layers, they are switches. If you have 3 layers, they are routers, which may be switches or routers. So, and there can be many. There can be thousands and thousands. Because remember, this, we call these nodes. So these nodes, okay, even these are also called nodes, but you're talking about those intermediate nodes. These nodes can be very many because normally a node, there will be a node where the limitation of the medium reaches. So you're going to have a node there. Yeah. So, for example, if it's fiber, if you are running fiber and it goes around 60 kilometers, again, you are going to see look at media to see the different capabilities. So if you are running fiber, you can be able to do about 20 kilometers, 60 kilometers without regenerating the signal so that they can now proceed further. Yeah. So in such a case, you find that most of these nodes will be around 50 kilometers apart. Yeah. For most technologies, to be around 50 kilometers apart, even the microwave, even terrestrial microwave. Of course, uh, if it is satellite microwave, it could be further apart. But if it's terrestrial, fiber normally to be about 50 kilometers apart. So if you are going up to the US, then there will likely to be very many switches. Yeah. Of course, it's not just a kind of a flat network. It's a bit hierarchical. Don't worry about that. I'm bringing that issue so that you just don't think these are just switches connected just in a string. There will be some hierarchy. There will be an autonomous system. Yeah. So in an autonomous system, so that will be, it will work differently than when you go from that. Internet is divided into autonomous system. It will be working differently when you are going to use different protocols. You still need switches and routers, but the protocols you are going to use will be different when you get out of the autonomous system and now connect with another autonomous system. Because if you are, for example, talking to some place in US, you are unlikely to be on the same autonomous system. The autonomous system is under the control of an admin at a very high level, probably an ISP. Yeah. So, well, even an ISP is controlled by the international body. So it's still controlled by IANA. Yeah. So you can browse and find what IANA does. You don't have to get into that. So this can be many. Yeah. So we would do only two, but there will be many. So these 4 layers deal with end to end. These 3 layers deal with node to node. So you are moving from node to node, node to node, node to node. Yeah. So of course, what happens is the user gets access to the network at the application layer, and therefore there will be application protocols. Of course, some of the application protocol will depend on what is your application. Yeah. So if you are running, for example, suppose you are running, you are sending email between A and B, then one of the protocols you may be using is simple mail transfer protocol. Yeah. Yeah. If you're using simple mail transfer protocol, what it means is that that application header will have this among other things. Yeah. Yeah, because we are going to look at headers from transport, network, data link. We are going to look at these headers to drive the point home. But we are not going to look at these headers at all these layers. But the headers at these layers will be having things like which protocols are being used between these two applications. So if you are using, if it's for email, probably you'll be using STMP. Yeah. And probably if this is of course for email, it will be running from our email. Our email uses what we call post office protocol. Post office protocol is something we are aware of. The user sends the letter to the post office, and the person, the other user who is about to get the mail, is that email or that mail, because in this case you're talking about the old post office protocol. We know the user gets the mail from the post office. Yeah. So you'll be having the post office protocol. So it may not be, B may not be the other user. So B may be for the case of SMTP, B may just be a mail server. Yeah. So in that case, here it will be running, it will be the client, it will be the server, this will be the client, this will be the server. So you'd have POP. Maybe you have POP3. I think POP3 is one of the post office protocol used with SMTP. Or this may be IMAP. Yeah. Yeah. So those are the kind of protocols you are going to find here. So you'll be specifying which protocol. So if you are using SMTP, then the header will be SMTP. If you are using IMAP, in the header it will be IMAP. Yeah. If you are doing network management, then probably your protocol will be SM. Oh, it's not SM. It's SN. SNMP, Simple Network Management Protocol. So there will be different protocols in different layers, and that's why we call this the protocol layer architecture. Yeah, or the network protocol architecture. The network protocol architecture, because there will be protocols at every layer, and those protocols are meant not for these people; they are meant for the peer layer. Person at the peer layer. Peer layer means this is a layer. I think this is a layer at its end. Yeah. So they're meant for some person at the other end who has this layer. And who has this layer? Only end to end would have that layer. Yeah. Okay. In these others, you only have these three layers. And this part which is not end to end, we call it the communication subnet. I don't know that we have discussed that. We call it the communication subnet. So communication subnet is referring to these three layers, which are going to be found everywhere, including in the intermediate nodes. But in the end nodes, you'll be having all the 7 layers. So application layer, it provides users and application processes access to network services. Of course, here you could be doing resource sharing, remote file access, remote print access, network management, directory services, electronic messaging. So what it means is, for example, trying to think what protocol you're using here. Let's think about, I can remember, of course, we had just talked about that one. Network management, simple network management protocol. If it is email, it's MSMTP. directory that will be DNS. I don't think, I can't remember which protocol you use with this. Oh, this will be maybe file transfer protocol, uh, trivial file transfer protocol. Yeah. So this could be different protocols. Yeah. If you are browsing, of course, that will be HTTP. Yeah. Hypertext transfer protocol. So these are the kind of protocols you find in application layer. They have to do with what functionality is being given at that layer. Yeah. So from there we come to the presentation layer. This one basically is, I think the name just says it all. It's like where you want to present uh, your data in a format that that is compatible with the underlying network. Because you may find sometimes you may either the underlying network, because uh, this network may vary, of course, down here it may vary. So there are some decisions you might have to make at this particular point in the presentation layer. Yeah. So you may need to do compression, for example. Yeah. You may also need to change your uh, your data to the format here, because we are seeing like the case whereby, well, where maybe your data is voice. So in that case, or maybe it's a keyboard. Keyboard I think is the best choice. If it's a keyboard, then your data has to be converted into zeros and ones, and then that you can use ASCII, you can use FCDIC. Yeah. This yes, you may want to, for example, you may want to do secure socket layer. I'm trying to think. This one again, this is used to when you're trying to access another network or the internet. So you may need to use some security. So you may have some of these functionality, some of these protocols depending on the functionality, and they are meant to communicate to this end. So if you are trying to tell the other end, we are using ASCII, we are not using FCDIC. So the other side knows that that's what we are using. There could be UTF. You know, this UTF is the most common, that to the universal, I think, telecommunication format. I can't remember UTF. Is a more, it has replaced this ASCII and FCDIC for this formatting of, let's say, keyboards, representing key characters with zeros and ones in binary. Yeah, because remember, everything that communicates in a computer network is in binary. Yeah, so whatever you want to do, you must convert it to binary. You need a keyboard which produces symbols. Those characters, we call them symbols. You have to convert them to binary. Session layer. This one is the one, I mean, to communicate between end users, you need to set up a session. A session is when you start communicating and when you stop communicating. And what will happen is when you stop, another user will start using that link, yeah, that connection. Yeah, so that is called a session. So this is the layer that establishes, manages, and terminates communication sessions between applications at each end. Yeah, so you want to send an email from when you start to when you end a session. Yeah, so it is the one that sees that you have stopped communicating and it terminates. And because of course what is happening is in this case we don't have channels. Even when you talk of multiplexing, the limitation will be maybe the capacity of that channel. So maybe the because of the bit rate, I mean, you're going to have more error rate. Uh, well, unlike maybe telephony, you see, in telephony, if there are no more channels to communicate, what you normally get is uh, is an engaged tone. There are no more channels to communicate, so you have to wait until somebody puts down their phone, and then you can get uh, a link. But you see, when it comes to IP communication, that doesn't happen, especially where we are not even setting the path. Doesn't happen. What happens is you keep on sending packets, but what would happen is, or there are no limitations to how many sessions you can establish. Yeah, you can have, you can keep on increasing the sessions, but of course, what would happen is they go up, then you're going to begin having a congestion in the network, and then you have to deal with that congestion. Yeah. So, but these are the protocols that manage that. Yeah, you can see the session control protocol. Some protocols will have names of what they actually do. For example, the first person who produces a protocol, he can call it anything. Other protocols now would have other names because they can't use that name. So session control protocol. This was by Microsoft. NetBIOS. Yeah, was by Microsoft. There is PAP, password authentication protocol. This one is used in point-to-point one links. Yeah, point-to-point wide data network links. So they normally use password authentication protocol, and there's still another protocol, CHAP. Challenge. What is it called? That's the problem of learning acronym. So there is CHAP. I think it's challenge. Trying to be what it means. Authentication protocol. Yeah. Then there is there is point-to-point tunneling protocol. This one is used with VPNs, virtual private networks. It just means a network that is actually tunneled through or rather your packets are tunneled through the internet as if you are connected directly. That's why we call them virtual private networks. It's like a private network, but you are just being tunneled. Your packets are being tunneled through the internet. You are not setting up a direct link between two points in the network. You are connecting through, if your routers have got this protocol, these protocols, then you can be able to create a VPN. If your routers are VPN capable, that is, they have these tunneling protocols, then you can be able to use a VPN like you're using a private connection. Yeah. Transport layer. This is where most of the activities happen. To do, but mainly this layer deals with end to end. Yeah, it controls what happens between end to end. Of course, it is an end-to-end layer because it is not present in the nodes. So this is the one that makes sure that the end, there is an error-free. Apart from error-free, of course, because error-free just means the bits arrive well at the other side. But it also takes care of things like sequence. Yeah, because as these packets go towards the receiver, uh, that is node B, whoever is receiving those packets, the order may change. So they also deal with things like sequencing. Yeah. So it's a very critical uh, protocol. It's a very critical layer 4. And by the way, up to now, our packets, we've just been calling them packets. Yeah. But now here, we begin calling them segments. Yeah. Now here, not begin calling them segments. At that particular layer, they are called segments. The PDU in there for is called a segment, because that's why you do message segmentation. Yeah. You must split it into whatever, no matter how long was it, what it was, you have been adding data to it, you have been adding headers to it. Now at this point, you have to segment it and then add a header at that particular layer. Yeah. So whatever you get from up here, which is a SDU for this layer, you must segment it to some segments, smaller units, which you pass to the layer below, which is the network layer. So it provides that, it also ensures sequence with no losses or duplication. And it's good to note, because most of what is being done in this layer for end-to-end is also done in data link layer, but for node to node. Yeah, we'll reach there, but it's good to note that whatever is done end to end, so whatever functionality you're trying to do end to end for transport layer is done for the, is done at the data link layer between nodes. Yeah, between nodes, that is moving from here to here, here to here. These are nodes, and therefore, while we call this the path, we call this the hop. I mean, the entire thing is a path. The path you take. Well, this is a link, and normally this is just a link, but this a path. A path could be this a link or a hop. That's why we call it data link layer or a hop. But one path may have maybe 1,000 links. Yeah. So let's come to this layer again, transport. So this is concerned with the message segmentation, that is chopping your message into segments. Yeah. Of course, what you do is at the other end, at the transport layer, at the destination, you need to reassemble those segments. Remember now, at the other end, this end you are going down towards what? Towards the wire, towards the cable. Yeah. Then from the cable you reach the other side, you go back. Yeah. That's what we are saying. So the segmentation you did here, you have to reassemble them again as you're going out. Yeah. There is message acknowledgement. Remember, we are talking about error-free process to process delivery. Again, I don't know whether I need to talk about this time, because it is tied up with something else we call session multiplexing. Why is because I've mentioned just process to process. Note, I do not say end to end. I say process to process. I will explain that when I come to session multiplexing, why I'm talking process to process and not end to end. Yeah. Is there anybody with a question so far? Because I've just been talking, assuming you're understanding everything, or you now that you have covered OSI in the past, you are good, so we can continue. If we lost you somewhere, it's good to talk, because I know once you're lost, to get back becomes quite a problem, because you'll be trying to understand what I've talked about, and then not even listening to what I'm saying. So if you have any question, it's good to ask. And for me, as I say many times, there are no ceremonies. You can raise your hand, you can just press the microphone and talk. If it's burning, and I will stop and listen. So, message segmentation, then you do message acknowledgement. Acknowledgement is very important when it comes to reliable communication. Again, you are going to see why I'm using the word reliable, because there are times you may not need to use acknowledgement. Yeah? You're going to see there are cases where you don't need to use acknowledgement, and therefore you are going to use a different protocol in this layer. So when you want to do acknowledgement, then there's a particular protocol you are going to use. But there are some protocols in this layer that don't require acknowledgement, and we are going to see that in just a few minutes. So acknowledgement is important. Provide reliable end-to-end message delivering the acknowledgements. What it means, acknowledgement is when a receiver receives the entire message. Actually, it does not even acknowledge the entire message. It acknowledges packet by packet. Yeah. When it gets a packet, it has to acknowledge that packet by sending back to the receiver, to the transmitter, the packet. Yeah, a packet, acknowledgement packet. Yeah, ACK packet. So if there's a problem, it means ACK will not be sent. Sometimes people think that if you don't receive, then you send a negative acknowledgement. But actually, a negative acknowledgement is non-reception, is not receiving acknowledgement, because the moment you don't receive, probably the channel could be faulty. It could be a problem, so you can't expect to send a negative acknowledgement and say, "Hey, I did not receive." Actually, systems normally use timers. I sent my packet a few microseconds ago. I've not received an acknowledgement. It must have been lost. So I assume it was never sent. And then I'll send another one. Yeah. So there's message acknowledgement has to be sent. It has to be done in this layer. Message traffic control is only straightforward. You transmit back off when no buffers are available. Again, we're going to see this in when we are talking of congestion control. Because again, I'll talk about that when we reach there. But when you do this message traffic control with end-to-end nodes, yeah, then we call it congestion control. But when you're dealing with node to node, we call it flow control. So flow control is done in layer 2, and congestion control actually happens in this layer 4. Yeah. So whatever things you do about congestion, they are dealt with this layer, because you are dealing end to end. Yeah. So that's why we talk about flow control and congestion control. Congestion control happens in this layer because it's end to end. Flow control is node to node. It happens in another layer. Yeah. So you back off when no buffers are available. Yeah. Because whenever you receive packets, whenever a node receives packet, including the end node, so that you can process your message, what will happen is you would store temporarily your packets so that you can end up making decisions what to do with them. And of course, you may also store them because as you're deciding where to take them, or maybe where to take them is not, you see, you're taking on a path. Maybe the previous packet has not arrived. So you can't even take something else to that path. Yeah. So it would happen that, or you want to forward it to another device which is not ready to accept that particular time. So normally you have buffering. You provide for that. For some buffering, but if the problem continues, those buffers may be full because buffers are memories. And you have a limitation how much a device can have, yeah, in memory. Yeah. Normally when you make devices, we don't give them as much memory like a CPU, like a computer. Normally they are a bit limited. Routers would have limited memory. So they have limited buffers. And remember, they're also storing routing tables in the same memory. So buffers may be full. And therefore, what happens is you have to inform the sender through some message, yeah, which we are going to see during when you're doing the congestion control. Through some message, you can tell the sender to stop sending. Yeah, I have no buffers. That's what we call back off. Don't send more packets because the buffers are full. Yeah. Session multiplexing. Yeah. What happens is between here, between A and B, the sender and the receiver, the final receiver, where the packet is going. Packets, you see, packets could be coming from A to B, they could be coming to another computer C, they could be coming to D. So the way you know they are going to B is because their address, the address we are going to look at when we come down here, this logical address, IP address, is kind of the marker for the packets. Yeah, where they are going is given by the IP. Yeah, so the one we are going to look at the packet structures. To bring this home, we are going to look at the packet structures. So if you have the packet, remember this one is not being sent. It's not being sent at this point. I think we better be very clear. When you say transport, we are not saying there's a packet that goes directly here. The packet must go this way, then go through the wire, then reach and then go up. So communication happens when the packet has gone and it has reached here. So it is this transport which is not interpreting what was sent here. That doesn't mean there's a direct connection. I think that one is, I've seen students thinking like that. It just means this is the message eventually is meant for this guy, so this guy will interpret. Now, so when this guy gets a message, the way you know it is for this particular computer is the IP, and it is a destination IP. So the packet that is sent, among the addresses it has a source IP address, and it's important because you need to communicate back, you need to give a reply, and then the destination IP address. So if destination IP address is the address of B, then that packet is for B. If the destination address is the address for C, then that packet is for C. And of course, that decision is made by the intermediate devices, which is the routers. And if it's for D, the destination address is for D. Now, what happens is there may be more than one applications. There may be more than one processes running between A and B. Yeah? But you see, all the processes running between A and B, the packets emanating from those processes would have the same destination IP. So if they are running at the same time, which you are talking about, that's what we call multiplexing. How do you identify which come from which process? Yeah. So there's another concept which is called creating sockets. And a socket is an IP concatenated with a port address. Yeah, port address is an IP concatenated with a port address. This is called a socket. So each application would use different sockets. And the socket is concept is very important. If you try to do configuration, in most cases, you're going to find that your network will not work. Your application will not work because you have not set the socket. These are common. Nowadays, I don't think there's a lot of auto configuration. So when we started doing networks, what was happening is, in most cases, you just because you didn't know the HTTP port address, yeah, which I think is 80 and that 128. You create your network, everything is okay, but you can't browse. Yeah. Because you have not done what? You have not configured the correct port address. So this combination of IP and port address is called a socket. So if there are two users, if there are two processes running between A and B, then they will be differentiated by the difference ports, because they will have the same IP, because they're on the same node. Yeah. So that's what helps us to do session multiplexing. You can have more than one session running. One could be a HTTP session, but you can't have two HTTP sessions running. Yeah. But you can have, because then they cannot be identified anymore. But you can have a HTTP session running with a SMTP session running, yeah, at the same time. Yeah. So I hope that concept is clear. Then there are two I mentioned earlier that there are different protocols, transport protocols, but we are going to look at the two most common. Because I think there is also a real-time transport protocol. We are going to look, there are many transport protocols, but the most common are actually TCP and UDP. Yeah, the difference being TCP is a connection-oriented protocol that a path has to be set before data is transmitted, while UDP is connectionless. So TCP is concerned about, first of all, you set a path, and it's also concerned about acknowledgements. Yeah, you don't have acknowledgements when it comes to UDP. So when you use UDP protocol, actually one of the things is a UDP header is smaller because it is not concerned about things like acknowledgement. Yeah. So you find that the header is not even concerned about sequencing. Yeah. It's not concerned about sequencing. So you find UDP is header is smaller. So sometimes it is used for efficiency. So for example, where you don't expect out of errors, you don't have to use TCP. You can use UDP because you don't expect errors, so you don't expect to deal with errors. So because whenever you cater for errors, you're adding headers. So you don't want to add headers to where you have no errors, you don't even use UDP. Where errors are not a major issue. Yeah. And I'll tell you where errors are not a major issue. If you're transmitting, I think I mentioned when we were talking about error control, if you're transmitting video or images, and a bit in error does not mean much. It just means one of your pixels will be maybe a bit darker than it's supposed to be. So your image will still be looking okay. Yeah. If it's a video, it just means one of those frames will be having one of the pixels. You're talking about a frame, not the whole frame. One of the pixels in the frame is probably a bit darker, or maybe it has more green than than blue. I think those are the colors. RYB, RYB. No, it's RGB. Yeah, it's RGB. So it has more red than green. Yeah. So it doesn't matter much. So you use the UDP. Where you're controlling equipment, while you are sending text, then it matters because if you change, for example, you're using ASCII and you change one bit, it will give you a different character. So you have to use TCP. So that is normally the work of the designer. Which protocol do I use? So you know your network, you know you know what you're trying to transmit, you know your application, you know the use case, and therefore you make the decision of the protocol depending on those cases. Yeah. That decision is made by the engineer, by the network engineer, you know. And when I mean the network engineer, I'm talking about not the people you meet protecting network. I've not probably, but they're not really network engineers. They're ones who are just connecting cables. The network engineering is a bit more. You have to understand the underlying protocols or the protocol being used in your network. Yeah. Basically, that's what you're supposed to do when you are an electrical engineer like current. Those are some of the decisions you need to make. Yeah. So we have already talked about. So I think everybody is clear about this TCP, and I think maybe I can just jump here to just drive a point home. This is a TCP packet header. The header is up here. This is the data. Data is what came from the other layer. So it means session, presentation, application headers, and the actual data will be inside here. So they are being covered by this header. Yeah. I didn't want to discuss headers, but I thought normally discussing headers makes one understand this fully. So we will discuss headers later. So That is the header. You can see it has a source port, destination port, sequence number, element number, data offset. I'll talk about those when we get there. Window, checksum, agent pointer, options, and padding. Yeah. Well, the UDP, UDP must be. This is a UDP header. Very little, just port number, destination number, length, checksum. Yeah. And I think this checksum only checks the, what do you call it? Yeah, checksum is used for error control. I think it's only for header. So you have minimum error checking. But actually, this one is just to help you that if there's an error, since there's no acknowledgement, if there's an error, just drop that packet. Yeah, and like in the other case whereby if there's an error, since there's an acknowledgement, another one will be resent. Yeah. Then after that, I'm moving a bit faster. But understanding of this, actually, the moment you understand this ISO model, that's the starting point for networking. You understand ISO model, it makes you understand, even if you don't do anything else, you have enough knowledge to work on the network. Yeah. But you're going to look at the details of the others. But believe me, this model is everything. When you look at what happens in the model, it explains exactly what happens in digital communication. Yeah. So the network layer, this one is concerned with the operation of the subnet. Remember, I'm talking about the communication subnet. This one here is concerned with this operation now here in the subnet. This communication subnet. Yeah. So it's concerned with the operation of the subnet, deciding which physical path the data should take based on network condition, priority of service, and other factors. Network conditions. That's why there's a device called the router in this. Now remember, from here you are going to have devices. So you remember we said all this up here was software. Now here we are talking about hardware. So now you're going to be having devices. Because this is now hardware. Yeah. So there will be a router, and the router does routing or routing. That's what we call this. When you decide the path based on the conditions or the priority of service and all that process we call routing. Yeah. That's what we call routing, and that's what a router does. A switch will forward a packet according to the destination MAC address. But a router, apart from forwarding according to destination IP address, it also considers the network conditions. Yeah. So the network layer provides routing, that's what it is. It provides a logical to physical address mapping. Again, a very important thing in that, remember, an IP address, we also call it a logical address. And what happens with an IP address? It can change. You can be allocated either by the admin, if it is a static IP address. If it's static means once it is set, it doesn't change. But remember, you can change it on your computer if you want. If you choose static, your admin can change it. And therefore, you cannot rely purely on IP address to forward a packet to a particular place. Yeah. Of course, if it's dynamic, it's even worse, because if it's dynamic means your router has got this capability, dynamic host configuration protocol. It has that software. What it is going to do is going to give you, every time you try to connect to the network, it will give you an IP address. It will give you a dynamic IP, which makes it worse, because even if your computer just goes off for a minute, even if the network just goes off for a minute, when you go back to the network, you are given a different IP. Yeah. So under those circumstances, it will be very difficult to communicate. So how does that happen? This device comes in. This software here is called ARP, Address Resolution Protocol. Is the one that does this mapping. Logical addresses into physical addresses. Yeah. I think this, I don't know how I put this is not even correct, because it doesn't do names. Can it do names? I think it can do names. In a LAN, these are some softwares that allow you to name a computer. Yeah, so it can use a name in a LAN, yeah. But normally it's logical address to physical. Why? Because physical is permanent. It doesn't change. Yeah. It doesn't change. The way I normally look at it is like a name of an estate, or a name of a street, or maybe someone's home. You can say it is on this street, this court, this house. But remember, the owners of that court may decide to change the name. Maybe a buyer has bought that and has called it a new name. But the physical address in this scenario would be there. Then what? What will be a physical address in this? What will not change? Ogola. In the case of a physical home, what do you think will not change? Even if somebody else buys the house or the estate and calls it his name, what will not change about that location?
Just the coordinates, the geolocation.
In the geolocation, that will not change. That will be equivalent now to the physical address, because physical address doesn't change. Actually, physical address can only change, like the old case, it could change if you change the card, the network card. It will change from your computer now. If you put a new card, now you be, according to the network, now you're something else. Yeah, that can change, because the physical address is ingrained in the network interface. Yeah, it doesn't change. It remains permanent. Once, normally what happens is most manufacturers of network interface cards, they have been given a network interface range. Yeah, and so they can only use what is within their range. So if you get a network interface card from one company, it would have a completely different MAC address. That's what we call the MAC address, the physical address, medium access control address, to be completely different. Yeah. So that's why we need that resolution by using ARP. So the network device in this layer is called the router. The PDU on this layer is called a packet. Sometimes we call it a datagram, but we don't like using datagram much, because datagram is associated more with user datagram protocol. Yeah. So it will tend to mean that it's only a datagram if what is contained inside is UDP. Remember, an IP packet contains a transport layer packet. So we like just calling it a packet. Protocols in this layer include IP. There are many protocols. IP, ARP, address resolution protocol. There will be very many protocols here. I can't remember many. Of course, there could be even IPX. If you are not dealing with IP, IPX is I think is by Nortel networks. Yeah, not Nortel networks. So it's not Nortel networks. What we call Novell networks. IPX. Yeah. In fact, I think it's the alternative, although we don't use it nowadays. Instead of the TCP IP, a protocol suite. We also have the SPX, IPX. So this is by Novell. Why Novell used to be very popular in the 90s. I don't never hear of them anymore. In fact, nowadays people do CCNA by Cisco. The courses that were being done that time for networking was Novell Networks certification. Yeah. I think your generation has never even heard of Novell. But they used to be the main people who are in networking. They have been dethroned by Cisco. And now Cisco is using those standardized IP and TCP, which are standardized by IEEE. Data link clear?
Hi, hello.
Yeah?
I have a question.
Yes.
Can you really categorize ARP as the layer 3 protocol?
That's I like that question. Yeah. I think some people call it layer 2.5. But I think it's closer to layer 3 than layer 2. RARP is the one which is more. The reverse one is the one which is layer 2. Yeah. So I find it, because since you don't have 2.5, in fact, sometimes one of the is calling it the 2.5 because it is somewhere in between. It's not a layer 2 protocol. So you may, in some books, they may tell you it does not belong to either layer 3 or layer 2. But when we are studying it, I think the closest it can be is layer 3. Yeah. What do you think?
Okay, for me, I may say it's a layer 2 because when you want to know the MAC addresses of the network, you need to broadcast the ARP packets to the computers in the network, and then the response comes as a unicast, and that is after you have known the MAC address of the computers that has received that ARP packet. So because it's a broadcasted packet, the request.
I can see where the
data link.
Yeah, I can see where the communication. I can see where the problem is coming from. Actually, the one we are discussing is RARP, which is squarely in layer 2, because this one is the one you broadcast when you want to know IP. You see, the ARP is actually inside the router. Yeah. This RARP is actually, there will be an RARP server, which you normally send. You normally send what do you call it? You just mentioned it. Broadcast. When you send broadcast, you're sending it so that also the RARP server can see it and tell you what is your IP. Because that's where you get your unicast. You are getting your IP So what you don't know is your IP. You know your MAC address, but you don't know your IP. And why do you want to know IP? Because you want to send a packet and you want to enclose inside the IP. Does it make sense?
Okay. I think the router doesn't process broadcast packets. It drops them immediately after they reach there, because it searches the route of the information based on, I think, the longest match of the IP address.
Yeah.
So when it receives the broadcast packet, it immediately drops them.
Yeah.
So the only thing that can broadcast is the switch. So based on layer 2 packet forwarding.
Yeah, I think we will talk about that. But I can see that some confusion is the protocol you're talking about is RIRP, not ARP. That's the protocol you're discussing.
Or maybe it is defined differently according to different vendors. Because
okay, can you call me later? We talk about this, because I can hear the discussion is you are actually discussing RARP, the one that does the opposite of ARP. This RIRP is
because for other vendors, they just say it is ARP.
Yeah.
They don't really go, like, they have different definitions of, I think, ARP packets. Because others will say it's broadcasted at layer 2 to identify the IP addresses and the MAC addresses of the devices.
Yeah, because you are saying everything about RIRP. So what I might suspect is probably the book you read, or maybe however you learned about it, the RIRP was being referred to as ARP, but ARP and IRP are two different protocols, and one is considered to be a layer 3 protocol, and the other one considered to be a layer 2 protocol, because they do the opposite. This one is telling you what is the, I mean, that IP address you have, what is the physical address of that computer. This other one is actually asking, actually it is like, what is my IP? Yeah, because I know my MAC address. What is my IP? Because you need it. You need it because you need to transmit. You need to enclose it in the packet which you are going to send out. Yeah, so you need to know it. Actually, it's like, who am I? Yeah, but we can discuss that later, because so that we can clear that together. But they are two different protocols. Yeah, and I think we already mentioned it in this document somewhere. RAR, no, it's not here. When you're discussing devices, we are going to discuss that RARP. So for now, maybe I can try to clarify later, or you can try to also try to refer to where you got it, because to me, there are two different protocols. Yeah. So let's continue, but it's good to hear that you already have looked at it before. And let's proceed. Yeah. Yeah, because there is a lot of confusion between ARP and RIRP. That's why I'm a bit worried. Yeah. So, but for now, let's take it to be a layer 3 protocol, and RIRP to be a layer 2 protocol. Yeah. Is that okay, Clement? For now.
Yeah.
I know I'm trying to convince you something you are convicted. Otherwise.
Yeah.
Kindly call me.
Okay.
I'm sorry, I may have left you more confused confused now, but we can check that later. Yeah, we can look at it together later and see where the confusion is coming from. So let's go to data link layer 2. This is the one that provides error-free transfer of data frames from one node to another. And this layer actually does exactly what the transport layer, but now it does it for node to node. Yeah, this does it from node to node, while actually the other layer does from end to end. So it is concerned with link establishment and termination. It establishes and terminates the logical link between two nodes. It does frame traffic control. So whatever traffic control we do here now is in the frame. That's why we are calling it frame. Whenever we talk about frame, remember you are talking about layer 2. It tells the transmitting node to back off when no frame buffers are available. It does frame sequencing, transmits and receives frame sequentially. So sequencing again is possible. Yeah. Of course, the only way you can lose sequence in this sequencing is when you send your packet. It gets lost. You have got A and B. So it depends on, of course, your flow control method. So you send a packet. So you have got, let's say, 2 packets, A and B, and then okay, I can't use A and B for both packets and for users. Let's say you have A and B, then you have packets X and Y. Yeah. So the packet X goes towards A. Yeah. And once the packet A goes towards A, it is lost. Then after some time, A finds that there is no acknowledgement. So so your packet A is sent. The packet X is sent. It reaches this side. It doesn't reach this side. Yeah. It doesn't reach the side. It's somewhere. Something has happened to it. But the after some time, it finds I have not gotten acknowledgement. So he decides to send X again. Yeah. So you have sent X, and then you send Y. Yeah. But then you end up getting X. That one which is not arrived. Of course, I'm trying to think of the scenario where it would have been in between. But somehow the same packet now X arrives. So you can see already now we have sequencing issues. Yeah. You already have received 2 packets of X. So that's why we can talk about sequencing in between nodes. Because it's not easy to imagine how does sequencing issues arise when you have only one link. Yeah, but you can arise because of that situation. Yeah. So that is dealt by this layer. Frame acknowledgement. Yes, we say there's also acknowledgement in a link. Yeah. Frame delimiting. Very important frame delimiting. In that when we are sending packets, Remember, these are just zeros and ones, yeah, being sent in a bit stream. So how do you know that a packet starts from here? Yeah, because you'll be having a string of bits. Maybe 0, 1, 1, 1, 1. Of course, there will be more than this. Yeah, there are many. So this will be very many. So in fact, even this will be in one packet anyway, because even when it comes to let's say an internet packet has about 1500 bytes. I think the internet frame has 1500 bytes. So it will have more than these bytes. But what we are saying is if you are reading a packet from here, it will have different meaning than if you read it from here. Or if you read it from here. You see? So it's important to know where does the frame actually start. That's what is called frame delimiting. There are various methods of frame delimiting. Of course, one of them is counting the bytes. Yeah. Because remember, in networking, just like in processing, in microprocessing, or rather even in computers, that's why we talk about this computer has got these megabytes. That addressing is done on a byte basis. So if its memory is byte addressable, if its communication is byte addressable. Byte, well, we might just call it a identification. You have got every byte has a number, what we call a sequence number. Yeah. So in that case, when you are trying to do frame delimiting, you'll be looking not at the bits, but at the bytes. So you know which byte is the one which is starting. Yeah. So because if you read from a different place, of course, bytes will have completely different meanings. Yeah. Or rather, the packets will have completely different meanings. Frame error checking. That checks the frames for integrity. That is similar to the error checking we do at layer 4, but in this case we are doing it at layer 3. So you want to check whether there's an error that takes place from one node to another one. Medium access management. Yeah, this one determines whether the node has the right to use the physical medium. So here again, medium access management, there are different medium access protocols. Yeah. For example, there could be token passing. Yeah. Remember we talked about a token ring. No, we haven't mentioned. Sorry. I think I was talking that with somebody else. So token passing is used by token ring. For example, the token ring protocol, which is a competing protocol with Ethernet. I think it's no longer competing. I think Ethernet has been accepted as the standard, the de facto standard. It is still, the de facto standard. It is still the standard according to the standard bodies, but it's a standard. But sometimes there can be the de facto standard where everybody is using it. Although, of course, de facto tends to be used whereby something is not standardized. But I think the one I wanted to use is the most widely used standard, the Ethernet. But token passing used to be used by IBM. I don't know whether they are still using it because I don't even see token ring circuits anymore. token ring networks anymore, token ring switches anymore. So it can be token passing can be CSMACD, which is used by Ethernet. It can be CSMACA, yeah, used by wireless Wi-Fi, yeah. Network devices in this layer are switches, bridges, and NIC cards, and network interface cards. We are going to look at this in detail when it comes to network devices. But of course, what happens is you can see we don't have a hub here, because a hub does not understand layer 2 addresses, therefore it's not a layer 2 device. These are only the ones that understand MAC addresses: a switch, a bridge, and an NIC card. Then of course we have the physical layer. Yeah. Physical layer. Yeah.
Yes, sir.
Yeah.
Can you clarify further what is MAC address?
Oh, MAC address. Yeah. This is the medium access control address. Medium access control address. It is meant for medium access. It is also known as physical address. Physical address. So every device that can access network, including your network device, I mean the smartphone, would have a physical address. If you go to your computer and you go to about, if you go to your phone and go to about, the phone, you're going to access, you're going to see a MAC address. If you go to your router, you your MAC address. If you go to your, of course, the router would have an IP address, but have a MAC, still that interface would have a MAC address. Yeah. If you go to a switch, it would have a MAC address. Yeah. So any device that can be connected to a network must have a physical address which does not change. It's called medium access control address. It normally looks like something like it's a 48 bit. So it will be something like maybe OA 01 1F FF. I'm not saying I don't like it to exist somewhere. Yeah, 001D. Yeah, so that is 48 bits, because this zero means 4 zeros. This I'm sure you did some number systems. So one of the most important number systems used here is the hexadecimal. Yeah, hexadecimal. So it will be in hexadecimal. So 0 in hexadecimal means all zeros. Yeah. A in hexadecimal is equivalent to 10. So that will be what? It will be 1010 in hexadecimal A. So when you write like this means 00001010. That is just OA. And of course, this next will be 00000001. The next one will be the next one will be 00011111. So I'm sure everybody knows this. So a MAC address will look like this. Yeah, it's 48, this 8 bits and 6, so 48 bits in binary. Yeah, and that is one which is in every card. That is the one you are trying to get with ARP. ARP is trying to get what is this what is the MAC address, yeah, of that particular person you want to send to, yeah. So it's important, yeah. It's very important for communication, yeah. So did I answer your question about the MAC address?
Yes, thank you.
Okay. Then this, I don't know, the TCP/IP model is just a four-layer model. I don't look at a lot about TCP/IP model, in that it's the functionalities are just reorganized in different layers. Yeah, they're just organized in different layers, and this is a four-layer model. This is how the functionalities are organized. Because you notice here now you have an application layer. You don't have, so this, if you compare it with the OSI, these three will be here. This will be application, presentation, and session. Then this will be directory, the transport. This will be network. Here we call it internet, but here we call it network. And this will be like the two of them, which is a data link layer and a physical layer. Yeah. Oh, sorry, I reached here, I did not look at the physical layer. Of course, physical layer is very important because the physical layer is the one that does what? Is the one that changes now. You see, you have been creating, you have been adding headers to the SDUs, yeah, to make the PDUs at every layer. So eventually you're going to have in this layer a frame which will be having that, yeah, which will be having that, what do you call it? Which will be having, you'll be having a frame that will be having, of course, the data link layer header. It will be having a network layer header. It will be having all the headers inside and eventually the data which you wanted to transmit. Yeah. Yeah. So what now happens is in the physical layer, data just goes in bits. Yeah. So now you begin, once you have formed that frame, you begin transmitting your data into the we call it to sending your data in zeros and ones, in bit by bit into the wire. So bit by bit, again depending on your encoding scheme, it will be converted into signals. Now it's the signals which are transmitted inside they are transmitted in the wire. Yeah. So bit by bit. Yeah. So this, some of the standards are this RS232, X21, EIA232. All these are different standards in this particular layer. But the main thing here that happens is the encoding moving from the zeros and ones into the signals which are now sent into the medium. So this is where also things, I think depending of course on whether you're doing electrical or optical signals, there will be different methods which are being used here in this particular layer. Yeah, because if you're using electrical, then you're going to have that data encoding. If you're using Optical, there will be a different data encoding. You are going to convert your bits using different methods into optical signals. Yeah. The network devices in this layer are referred to as hubs and repeaters, because these ones don't understand MAC addresses. When you start looking at the devices, what we have is a hub. We're going to look at the details. A hub just forwards the packets into every port. Yeah, when they receive the packet, they forward it into every port because they are not intelligent, so they don't know where to forward it. They just forward to every port, and of course, it means they go to every computer which is connected. It is a computer which has got the NIC, which is intelligent, that decides that this is not my packet. The switch, on the other hand, is intelligent, so it sends the packet only to the node where the computer is communicating with is connected. Yeah, but we are going to look at that when we are looking at the detailed network devices. When you look at network devices in details. So, any question up to there? So, if there are no questions, I think for this model, the only thing I want to look at, maybe to give you a good, you can look at it at your own time, but I think I'll just talk about it more. I'll just look at one packet, for example, so that you can understand the packet, the concept of packet communication. Otherwise, I do want to look at this for your case, because we are trying to just study enough to be able to design our network. I don't think you need to go into the packet structures, but we can look at one packet structure just to give us an idea. Then we can jump to the devices. Yeah. So this is the packet structure. This is for TCP. This is for TCP/IP model, but it will be the same also, because remember the transport layer is almost the same for both models, for both the ISO model, the OSI, and also for TCP/IP model, the network model. The internet model. We call it the internet model. Internet model, DID model, TCP/IP model is the same model. That is a model which is 4 layers. But this packet is covered under the transport model. I mean the TCP/IP model, and there is a transport packet. The transport packet, of course, is this entire thing, but the transport header is this particular part. This data is just going as one line, but this is a lot of, because remember these are just 32-bit words. And again, we do it like this because it's supposed to be a long packet. It can't fit in the page. So what we try to do is we do it as layered. Of course, it's not layered. Yeah, we do it like it's having different layers, but it's not layered. It just means this goes from 0 to 31. Then it continues here. It continues here. It continues here. It continues. Then it continues the data, and there's a lot of data which has come from the upper layer. So, looking at the header, you can see there is a source port and the destination port, because remember we have the port address in this layer, because this port address is the one we use for multiplexing. Remember, we're talking about multiplexing. We use it for multiplexing, We also use it for NATing, network address translation. Yeah, NATing, when you want to use a single network connection which has got a routable IP address, or rather internet routable. Let me just put it that way, internet routable, because private addresses cannot be routed on the internet. It has internet routable addresses, but here we are using private addresses inside the LAN, inside the local area network. Yeah. So so you need these two port addresses, and because these port addresses are what? Are 16 bits. Yeah, from 0 to 15, that is destination port, and then from 16 to 31, from 0 to 16 is the source port, to 15 is source port, and from 16 to 31 is the destination port. Then there is a sequence number. This sequence number refers to the sequence number, the first byte of the segment. Yeah. Remember, this segment has a first byte. So this is the first byte. Yeah. Actually, they go like this. I said they go like this. No, they go like this. Yeah. So this is the first segment. You want to see the first segment? What you're talking about, the port number, I mean the number we are saying, although of course this is a source port, it consists of bytes, and the bytes themselves are numbered. Yeah. And they are not numbered. Actually, this is number 1. It is a data stream. From when you start sending that stream. Yeah. So that first packet would have a number, and the number may not start from 0. Yeah, but you have a number. But the number we are interested in, the sequence number, is the number of the first byte of this particular packet, of this particular segment header. Yeah, I hope there is no confusion there. Yeah, because you'll be having a lot of data following one another. Yeah, and it will be maybe it's a long one like that. So there we are. So these are packets. No, these are not packets. These are the bytes, the 8 bits. These are the bytes. So these bytes have numbers. Yeah. And that number, the number which is given in this sequence number, is the first byte of that particular segment. Yeah. So it means it could be starting here. So if it's starting here, this number is this number here. Yeah. If it is starting here, the number of this, put this as a number, it will be the number you put here. That is a sequence number. Acknowledgement number. This normally is a number. You are acknowledging this packet. It is the last byte of this segment. Yeah. So if the segment was coming from, let's say just for starting from here. So this is a segment itself. So this acknowledgement number will be, now it will be for this packet, but it will be in the packet going the other direction. So if this packet goes to the other side, Now, the packet that's coming in this direction, the acknowledgement number will be this number. So when you get acknowledgement number of this packet, it means you're talking about the last byte of the segment that had arrived last. Yeah. Then that becomes the acknowledgement number because you're acknowledging that packet that just arrived. Yeah. Is a way of piggybacking acknowledgement. Yeah. So you want to know the other, you are telling the source the packet arrived. So this acknowledgement number is the acknowledgement number of the, is the last byte of the packet of the segment just received. Yeah. Then there's a data offset. Data offset, this one is telling us where. So this one actually gives us another offset. You can see these are 4 bits. It's simply telling us where our data starts here. So it will either be reading 5 or 6 because data offset is in 32-bit is in 32-bit words. So it is how far from the start is the data in 32-bit words. So if it starts here, that will be 32-bit. How many 32-bit words is 32-bit? 1, 2, 3, 4, 5. Or if it is 5, 6, then the 4 bits. So actually these bits we would normally read 0101 or 0110. These 4 bits. This is data offset. Yeah. We'll be reading one of these. Because it's telling us that it is your packet starts here if you have no options and padding. Because this is optional, options and padding. So it will reach, it will be 5 for a normal packet without options and padding, and the one which has got options and padding would be 6. Of course, what are options? Options, we are saying the standard TCP packet does not have options, but you may want to have extra functionality in that packet. You may want, for example, to have a timestamp. So if you have a timestamp and other facilities, other functionalities you want, then you include them, you add them here. And when you add them here, what you do, if whatever you added is not 32 bits, you have to do some padding. They're just zeros. So you pad, and then so your data must always start in a multiple number of 32-bit words. So it's either 5 or 6. Then the next one is reserved. These are just reserved. This code, these are 9 bits. We will look at them. So this is 4, this is 9, I think these are 16, so this must be 3. Yeah. These 3 are reserved, they are not used. 9, these have got different, we will look at them again because we are only trying to look at the concept, but you'll have things like reset, acknowledgement. Yeah. Acknowledgement, we'll be trying to say that this packet is an acknowledgement packet, because sometimes you may just send an acknowledgement packet itself, not necessarily piggybacking. Yeah, actually, even when you piggyback, if there is acknowledgement here, you're going to say that this is this will read, acknowledgement will be set. Acknowledgement, reset, agent, maybe this particular packet is agent, it belongs to some agent application. Yeah. It has 9. We won't look at all of them, but that is the whole idea. But it has got the most common used ones are 6. Yeah. The other 3 are for congestion control. They are not normally used in most packets. Window, This one you're telling the person you're sending the packet that this is the size of my window. Yeah. So they can know how many, so that when they are sending, they know the size of my window. Yeah. So my receive window, how big is my receive window? So that number is here. So the other guy, when he's sending, he knows how many packets he can send continuously, probably about 24 acknowledgement. Yeah. So that is the window. You need to know, the guy at the other end need to know what the size of my window. Checksum error control. Agent pointer will be, that will only work if you have something, if the edge, I said this 9 codes, we call them also flags. These 9 flags, all of the flag is, as I said, is agent, URG. So if URG is set, then you have to say where that agent, the agent pointer. Because remember, again, this is a packet. This packet may not be, actually, this packet may not be carrying even the, it may not, because remember you have created segments which may not necessarily correspond to a particular, what do you call it, to a particular application. So you also need to show exactly where is the agent data. That's what's the number, that where you need, what do you call it, what's the best? Actually, I'm not getting this. Where the agent information starts from. I think that's what should be the agent pointer. Yeah. Options, we have talked about it. Padding, we have said you pad depending on the options. Data is what came from the upper layer. Yeah. In the case of TCP, is what came from the application layer. In the case of, that is TCP model, is what came from the upper layer. In the case of ISO model, is what came from the session layer. So I think for that, okay, maybe we can look at this, because again this only happens with TCP. Because remember, we see TCP is a connectionless, is a connection-oriented protocol. So we have to send sync fast. We have to do this three-way handshake by sending a synchronized packet to the host, and it is who sends a sync acknowledgement packet, sync ACK, and then you send a NAC, and then a link is established, or the pad is established, and you can now begin transmitting your data. We call this three-way handshake. It does not happen with UDP. It happens with only TCP. That's why we call it a three-way TCP handshake. So that is the order you send the sync, TCP synchronized packet to B, B receives and then sends back sync ACK, yeah, and then receives sync ACK and sends ACK, and that's when TCP socket connection is established. Again, you can see we are talking socket connection because it is the socket, a combination of IP and TCP. And now you can communicate. So any question on this particular topic before we go to today's topic? Because we don't have much time. We can decide either we have a small break and then come back and start looking at network devices, or we continue. I don't know which is which. What is your proposal? We continue for about 40 minutes, or we have a small break of 5 minutes, then we can come and continue.
Kindly let's have a short break.
Okay, let's have a short break. How many minutes?
5.
5. Let's continue at 11:11. Thank you. At 11:11, we continue. we are going to look at network devices, different network devices, and before we broke, I think somebody had asked about the ARP, whether it should be a whether it should be a network, whether it's a network layer protocol or is a data link layer protocol. I just checked. I found that actually it can be considered to be both, but it looks like the data link layer protocol seems to be generally accepted as where it belongs. So I think, Clement, you could have been right. Actually, you are right. It is more of a ARP. It's more of a data link layer protocol. But actually, in most textbooks, it is sometimes referred to as a network layer protocol. But I was trying to check the general because I checked very many sites and I found it was coming. Some sites were saying it's in between, so you can't define as any of them. But I found, I think, more sites going with that it is more of a data link layer protocol. So Clement, you are right. Yeah. Is that okay?
Yeah, it is okay.
Yeah. I think the one it is considered to be fully layer 2 protocol without any argument is normally the RIRP, the one that does the reverse. But I've also seen that also in some books they refer to just ARP that does both. Yeah. In some cases, it is specified that there is ARP and there is RIRP. So that could also be a confusion of where it should be, because where ARP is looked like it does both of those functionality. Finding the IP from the MAC or finding the MAC from the IP, then it is query would fall under layer 2 protocol. That's having clear. Yeah. So we can proceed with the network devices. So functions of network devices. What will be the functions is mainly to either expand your network or segment your network. Yeah. So expanding, that is if you want to add more devices in a network, what you do is simply add more switches. Yeah, you can keep on adding more switches so that you add more devices. Because most, for example, if it's switches, most switches would have, by now I think most of the switches are up to 48 ports. Yeah, so if you have got more than 48 users, you may want to add another switch. But normally switches, they start from 4 ports. Normally, even can get 6 ports, but they normally seem to be just doubling 8 ports, 16 ports, 32 ports, 48 ports. And sometimes you might get just some which are somewhere in between. Yeah. So the main functions is to either expand or segment. So we are going to see, as of course, as you expand, it also means you are expanding the broadcast domain. Yeah. Especially if you, for example, you are using hubs. As you increase it, you increase directly, you increase the broadcast domain. And you may want, because broadcast domains would also mean that there will be a lot of traffic in between. So when you have more computers, of course, the broadcast domain communication becomes more. So sometimes you may want to cut off I mean, or to divide that network into two, so that you create two broadcast domains. So the packets which don't have to go to the other domain are not seen by those computers. Yeah, that's what we call segmenting. So it may be for expanding or segmenting. So we are going to see which devices are used for expanding and which are used for segmenting. So the devices we are talking about could be the network interface card, which has to be present in every device that is connected to the network. It could be a hub. A hub, as we said, is just a device that is not intelligent, and basically what it does when it gets attempting to do it, I can talk about it in details. Let's say it's a small 4-port hub with the computers connected to it. Yeah. The computers connected to it, and what we have here, let's say these are A, B, C, D. A wants to send a packet to D. Yeah. Remember, this A could be up to 100 meters away. So as you are sending, when you send your packet, and please remember, when you talk about a packet, we are talking about many bits. So in a wire, they will go as bits. But when we normally say we are sending a packet, because all the bits will arrive at this end. What is it does? It forwards the same bits to here. Yeah. But of course, what it's going to do, those bits who have been distorted, they have changed the shape. They also have been attenuated. They have changed in the amplitude. The voltage would have reduced if, for example, you are using you are representing your zeros and ones as different voltages. So what will happen is when you get those bits, then you are going to forward those bits here. And of course, when they reach the computer, of course, they will be organized again. They will be organized into packets. Yeah, the bits will be organized into a packet. They will be buffered and organized into a packet. But that happens with every node. They go to every node. So first, they will be regenerated and then sent to every node, and therefore they can go to every computer which is connected to that node. Yeah. Now, of course, if D itself is trying to send a packet to B, it also do the same. It will go to every node. So there will be collisions between those packets. Collision in this case means their voltages mixing with one another. So there will be collisions, and what happens is if there's a collision, you may not end up recognizing those you may not end up recognizing those packets will be distorted because collisions means maybe two voltages are combining, and therefore the resultant voltage will represent neither 0 nor 1. Yeah. So it will just be, you see the packet will drop because the packet will be made up of those distorted pulses, or those distorted zeros. Because what happens, of course, once it reaches where it is going, it's converted into into 0 or 1, and the error mechanism will kick up, and of course it will find the packet is not the correct one, and it will just end up dropping it. Yeah, so that's what is going to happen now. It is received by B will find that it is not. So it's not exactly what was sent, because there will be some error checking mechanism, and it's going to drop that packet. So there will be a lot of dropping of packets because of those collisions. Yeah. So as the network increases, you find you can't just keep on adding more hubs, because what you could do is you just create a kind of a flat network. You could decide. I need to remove one of these. Yes, you could decide what you are going to do is you are going to just connect another hub. Yeah. Now, of course, we are going to connect another 3 computers. So if you have 6 computers and you only have available these 4-port switches, you end up using that. You can only connect a maximum of 6, because you're going to use this link to link up the hub. Of course, if it is the hub, what normally happens to the hub would have an uplink. Yeah. So maybe you could still be able to connect another one if your hub has an uplink. Yeah. Now, what happens is if A, let's say this is A, B, C, D, let's call the ones here X, Y, Z. If A wants to send a packet to B, to D, oh, this was C, let's call it C. To C, what will happen is the packet will be sent here. It will be sent here. It will be sent here, therefore it will come here. It itself is going to come here. It's going to come here. It's going to come here. It's going to come here. So this packet, although it will just being sent to C or even to B, it will end up going to also to X, Y, and Z, and it will end up colliding with the packets which X, Y, and Z are trying to send. So that's why we have a device called a bridge. Yeah, because a bridge is intelligent. Remember, we said a bridge is a layer 2 device. A bridge can understand layer 2 addresses. So what we have, instead of having this arrangement, we can have a network bridge which comes in between here. Instead of having this arrangement, you are going to work through a bridge. So this will connect here to the bridge. Yeah. We will change the color of this. Yeah. So now what you're going to do is you're going to connect a bridge here. Yeah. And what a bridge does, the bridge does not forward packets which are meant for any computer on this side. It will be dropped by the bridge. So what the bridge does, if A sends a packet for C, remember these packets have a MAC address. Although the hub is dumb, it doesn't understand MAC addresses. The packets themselves have got the MAC addresses, so it will come here. And when it comes here, it will be sent to all these guys. But when it reaches this guy, the bridge is intelligent. It will look at the packet inside. It will look at layer 2 and find that the MAC address is for C, because it is going to be maintaining a table of ports to MAC address mapping. So it is going to drop that it is going to drop that particular packet. It will not forward it to this other side. But if it finds that that packet, that its destination address is for Z, for X or Y, it's going to bridge it and now take it to this side. So you don't have unnecessary collisions which are being caused by the fact that the hub is not intelligent. So during the era of hubs, we used to have bridges. Yeah. You can still bridge nowadays for different reasons. Because you still have bridges today, but they're not working with hubs. Yeah. But the original bridging concept was with this with hubs, and that was being used to segment this network. So now this initially with the initial connection without this bridge, this was one broadcast domain. At the moment you put a bridge, you have created two broadcast domains. Yeah. So the devices you find are these bridges, switches, routers, or gateways. Yeah. These are the ones that do segmenting. You can segment with a switch, because you are going to find that actually a switch is a multi-port bridge. Yeah. Because that's what a bridge does. Because it does now on every port. Because it only forwards packets meant for that particular computer. And if, of course, sometimes you will find if this is a switch, now this is a switch, this could be going to another switch. So you find that's why we call it a multi-port switch, because it will send a packet. If a packet comes here from some computer, it will only be taken to where it's supposed to go. If it's going here, it will go here. If it is going here, it will go here. If it is meant for a computer which is here, it will come to here. Then it goes here. Yeah. And then this one will forward it to a particular port. Yeah. So we show this as a bridge. I mean, a switch is a multi-port bridge. And actually, a hub is a multi-port repeater, because before we had hubs, we used to have repeaters. Only two terminals, only just repeating the signal. It comes up to 100 meters, then it's given another 100 meters. So when you see the word repeater mentioned, you don't see it nowadays in computer books, because we no longer even use hubs. So we don't even use repeaters. So a repeater used to be a multi-port hub. Sorry, a hub used to be a multi-port repeater. A repeater had only two terminals. And a hub, I mean, a switch is a multi-port bridge. Yeah. So the interface, the network interface card, obviously is only a two address. I mean, there are two devices, because they have to understand MAC addresses. Because it is the one that understands this packet is meant for me. The computer itself does not understand the MAC. It is that device network interface, which is becomes part of the computer. I say becomes because sometimes there can be an actual network interface card. That's why we still use the network interface card, because the original are cards which are not part of the computer. So they used to be connected to the computer through an interface like the PCI. Yeah. But nowadays, most of the computers we have today, they have a built-in. They have a built-in network interface. Yeah. So hubs work at OSI physical layer. Sorry, where am I going? So network interface card will be found in every computer. They understand MAC addresses, because they only take packets which are meant for that particular computer. Who owns that network interface card? The hub, these ones operate at the physical layer. We see their physical layer devices because they don't understand their two addresses. Of course, they can connect different media, so you could see hubs which used to have a coaxial interface and also the standard interface you are familiar with, the UTP interface. Yeah, the RJ45. They can take the RJ45 or they can take the BNC cable. Yeah. Hubs cannot join segments with different access methods. So they cannot, for example, join a segment which has CSMA CD with one which has a token ring. Yeah, using token passing. Yeah. So CSMA cannot work with token passing. It is used by token ring. Hubs do not filter packets because they have no basis for filtering packets. They can do policy filtering where you filter based on a certain, either it can be MAC address or IP address or application. So they can't filter packets. That's why the packets go to every computer, and now there's a computer itself that decides this is my packet. The hub does not do that. So that's a hub with a coax interface and UTP interface. These are TP cables, and if you connect something here, that will be connected through a coax cable. Yeah. Bridges, I think we have already looked at bridges. We said they forward packets based across the bridge based on the MAC address, the destination MAC address, where that packet is supposed to go. So that's how they stop the packets which don't have to go to this side. Yeah. What has happened? All of a sudden, my document has now let me open it again. My document has lost the network devices. Just 1 second. It's, document. Yeah, we are looking at hubs. Here we are. We have looked at bridges. Yeah. That's how a bridge works. To just forward what belongs to segment 2 through the bridge. So it creates two um, collision domains. Yeah. Otherwise, if you had connected this with just a wire without going through a bridge, that will be one collision domain. Now, switches, of course, what they do is they forward based only on the MAC address. So when a packet lands on a switch, on a port of a switch, is forwarded to only to the port that contains the computer or the computer, yes, which has, well, it can be the computer, it can be even the device, which has got the MAC, whose MAC address. Because remember, this MAC address can be an interface or even a router. So that's why I don't use a computer. So whose MAC address is the same as the destination address on the packet. Yeah, is the same as the destination address on the packet. Yeah, because the packet has got a destination address part and a source address part, and we'll talk about this destination MAC address. So switches are basically multiple bridges that can interpret MAC address information. Switches divide network into several isolated collision domains. Yes, because every port belongs to a different collision domain. Yeah. Packets to a particular MAC address is sent only to the port AR. Advantages: divides network into several collision domains, reduce the possibility of collision. Collision only occurs when two devices try to get access to one channel, which again is handled by something different. It's handled by the network access method protocol, whether it's CSMA. It handles that. Yeah. Data will only go to the destination, but not to others. Switches can logically, yeah. With the switches, you can create VLANs, virtual local area networks. I don't think we look at VLANs. Yeah, we won't have the time, so you can look on your own what VLANs are. You won't get time to look at the VLANs. Switching methods. The most common switching methods in a switch are three. There are many, but three are the most common. One is a cut-through mode. Cut-through mode just means that the packet is not, you don't read the entire packet. You only read a part of the packet. You read the part that up to where you can get the destination address. You just read enough of the packet. By read, it means going through the bits. You only read enough of the packets to let you forward the packet. Yeah, and this for Ethernet. For Ethernet, it reads only the first 14 bytes. And mind you, this is for Ethernet. It's not for every. For Ethernet, it reads the first 14 bytes of each frame. The preamble, destination, MAC address, and then transmits the frame. I think I should have, yeah, here we are. This is how our language frame looks like. It has the data. So the data is basically, okay, this is a TCP IP. This is when you carry Ethernet. Because on the internet, although we are using ISO OSI model for teaching. In the actual, and probably that could also bring the confusion we had with SAGWA. In the actual networks, we actually work with the TCP/IP model, the layer 4 models. Yeah. So we use this layer. I think because the concept of layering is more understood with the 7 layers, because you have more layers, so the concept is more understood. But in the actual internet, actually what we have is only 4 layers. Yeah. And so that's why you can find we're only talking about application data that is covered by TCP, and then of course the IP from the network layer, yeah, TCP from the transport layer, IP from the internet layer, yeah, internet layer, that's what we call it in the TCP. In the OSI, it's called network layer, but it's called internet layer. So there is the IP, yeah. Then, so that data is now covered with this is given this header. Now, interesting enough, in layer 2, we normally give it the header and a trailer. Yeah. So that is this what has come from the internet layer, and it is so what at that point you got the IP datagram. So we are giving it this header. So what we are doing in the case of cut through, we don't have to look at everything. You don't have to go through it. You just first of all read the preamble and destination mark. That's how you take the 14 octets, the 14 bytes. Because you have the information, you just forward it now. Of course, what happens with this, if you have a problem somewhere, you won't know, which you would have known if you read the whole packet. But now you won't know. So you can forward packets which have errors in the case of cut through. So cut through, the switch reads only the first 14 bytes. The preamble and destination MAC address then transmits the frame. It's obviously faster than store and forward, because now with the store and forward, you read the whole packet. So it takes time to read the whole packets. You read 1500 bytes, but here you're only reading 14 bytes. So it takes time to read through the data. Not only that, the moment you read through the data, you get to CRC. You see, where was I here? You go to social basis can be written as CRC or frame control sequence. In the case of Ethernet, our frame control sequence is CRC. So it has to read up to here, then carry out a CRC check before you can forward the packet. So it is definitely slow, but then you cannot forward packets which have errors. Yeah. So cut through cannot detect corrupt packets and can therefore transmit corrupt frames. It's normally suited for smaller groups, LANs, yeah, and small LANs for that matter. Yeah. Store and forward mode, the switch reads the whole packet before transmitting it. Corrupt packets can be detected using frame check sequence and therefore not transmitted. Is slower than cut-through switching because that's really the whole frame and carry out error checking. But due to their buffering capability, yeah, of course, you have to do buffering because in the other case you don't even need buffering. Yeah, because you are only reading just do small buffering up to 14 bytes and forward. But here you need to, because of this buffering capability, you'll be able to connect segments in the different speeds. Yeah, more suited for large LANs since they will not propagate error packets. Adaptive cut through makes a lot of sense if, for example, you can use cut through, but then you find that since you have monitoring devices, you have network monitoring devices, you can get information from network monitoring devices that there are no errors, there are no requests for retransmission, and when that happens, you can actually, that's what is called adaptive. You can decide to use uh, cut through, but if you find there are errors, you can decide to work with store and forward. So this one moves in between store and forward, depending on whether there there are errors. The network monitoring software is establishing whether there are errors or not. Yeah. So that's the Ethernet frame, just to demonstrate that. Any questions up to there? Yeah. I was thinking when you look at the router, there is not much. I think maybe I can just talk about routers. So until next time, we just look at the network media. Let me just finish in those 5 minutes. The network routers. So routers operate at the OSI layer or layer 3 of the network layer, the network layer of the OSI model, and they operate in the internet layer of the TCP IP model. So routers route based on IP addresses and routing tables. So it will be, they will look at the IP address, but they also look at the routing tables because the routing tables will tell you um, which route is the best. Yeah. Now, I think let me talk about routers because I think I need to say more about the routers without going deep for you to understand this concept. And of course, there is also layer 3 and the gateways. So I don't think we can finish, and we have been on for 3 hours. That is quite something. So I think, in my opinion, let's stop there. And I think we have got 2, 3 more weeks. So I think we should be able to finish this. I was also intending to, as I said, I will give you a second assignment for designing a network. It's not meant to be a punishment, it's just meant to probably Sorry. Sorry. I somehow got locked out. I don't know why. So I was just saying that we continue. We can't finish. So we just continue next week. I believe we still have got 3 weeks. So I think we'll be able to finish. And as I said, I also give you an assignment on network design, a second assignment, which hopefully will give you more insight into computer communication networks. So thank you very much for that sacrifice for our class during holidays. So thank you for that, and let's meet next week. Have a good day. Is there any question? Maybe somebody had a burning one? Yes, somebody with a burning question? Yes, Samuel?
Yes, it's I'd say it's maybe a suggestion or maybe a question.
Yeah.
So for the last 2 weeks, we've been going to the telecoms lab. We're trying to configure some form of network. There are switches, there are routers, there are some BTS and antennas. I don't know if that counts as or maybe if it could be supplemented by the kind of assignment you want us to do. We can kind of combine it.
I see. Yeah, okay, it was a very general design assignment. Probably not dwelling so much on network configuration, but I'm glad to hear that you're doing network configuration. Yeah, but it was more to do based with the choosing protocols, choosing which media, choosing which device you need. But I'm happy to hear that you're doing configuration in your labs. Yeah.
Yes, for about 3 sessions, and if I'm being honest, personally it was a bit new because we had to deal with the MAC addresses, IP addresses, etc. So
you to do it?
It was a bit challenging to me.
Last week was a bit challenging. So I think now we have a better understanding. So I think if we are still doing the labs, it will be easier. But we'll see our hours, we can't go very deep. I thought in that this is just a topic of your computer of your unit. So we'll make it as straightforward as possible in the design. We configure basic configuration. I think is good to understand, but I don't think in our assignment we will dwell on the configuration of networks, because we could do that, but you need to understand also the use of, I don't know whether any of you or most of you have used packet tracer. Yeah, but I guess for those who may have done Cisco CCNA, then likely you have used a tracer, but if you haven't done CCNA, then you may not have used it. So we may not go into network configuration. Yeah. But it's a good idea to learn configuration, because at the end of the day, that is what we are going to meet out there, especially if you are employed by any company and you are the electrical guy, they will be expected to be doing the networks. So not like it will be an IT guy, but who does basic network administration. But when they come to something like maybe serious configuration or design of the network, they may want to rely on you. Yeah. So, but it will be a very easy exercise. You don't have much time. We are not looking into computer networks in depth. Yeah. So we will not go into configuration as such. Yeah. Any other point? So if there's no other question or concern or comment, I think we stop there. Let's meet next week. Enjoy your May Day, your Labor Day, and your coming weekend. Thank you.